So thanks for joining us today. We're going to be discussing large-scale flash purification, sample loading method development, and scalability. And our outline for today, first we're going to start to discuss considerations for large-scale purifications, how they may be different from small-scale purifications and kind of the process involved with that. Then we're going to talk about different processes for method development based on those goals, different issues to consider when scaling up, and then how we can increase throughput with the Combo Flash Torrent. And then finally, in the end, we're going to kind of show an example of how the Torrent can allow you to run sequential injections uninterrupted. And so to start with here, we're going to start with large-scale purification objectives. So these are the kind of things that we need to consider for our purification and kind of questions you want to ask yourself regarding your sample. And this would kind of dictate kind of the amount of investment you want to put into your purification process. So first question, is this a one-time batch or repetitive process? Are you going to be doing a lot of different samples, one-time kind of sample batches, or are you going to be doing a repetitive process of the same sample over a longer period of time? So how often is the process going to be repeated? And then what is the amount of compound you need to purify and relative to the column size you're intending to use? So this is ultimately going to lead to the number of injections. Next, you're going to have to look at the isolation. What are your purification goals? Are you just isolating a single compound, or maybe you're just looking to remove an impurity from the sample matrix? So that way you can maybe do an advanced purification. Maybe you're doing a additional purification step later that's higher resolution to resolve closer impurities, but you want to get rid of a predominant impurity from the rest of your sample so you can load more for future separations on your prep HPLC or maybe even prep SFC system. And so how pure is the initial sample to be purified is another question you need to ask yourself. If it's relatively pure, then you're usually able to load more of that sample on there. And then how close are the impurities to your compound? What's your necessary resolution? How pure does your target compound need to be? There's some labs that we work with that have very strict purity standards up to 99.9+% for some of their compounds, while other applications may not need that kind of level of purity. Next question is, how can I load my sample? What's the solubility of the sample? Are we going to be doing a solid load cartridge, or are we going to be doing a liquid injection? Depending on your answer there, it's going to dictate what your options are for your process and maybe what your purification and resolution outcomes could be. And then finally, we're going to discuss the importance of cost purification. So obviously, depending on your stationary phase, your column cost could be a significant investment if you're using a modified stationary phase like a C18, C18AQ, C8, or mean column versus using a bare silica column. The investment at that point would kind of dictate maybe what size column you're doing, how many injections you plan on doing, and how often you plan on doing this process. If you're just doing one sample, maybe it'd be more cost effective to do a smaller column, but maybe do multiple injections on that reusable C18 or C18AQ or whatever your stationary phase is, and do multiple injections. Now, if you're doing that same process over and over again, then maybe you want to maximize your loading so you can get more done, and you end up having savings from your labor costs. And the other thing is your solvent usage too, is to consider when you're doing your large scale. So how am I disposing of the solvent that I'm using? What kind of infrastructure do I have to, limitations maybe in the lab on the amount of solvent that I can use if I'm using flammable solvents, because you're going to be using a larger amount of solvents with larger columns for purifications there. So if we're doing a one-time batch purification, so say we've got a large batch of sample, we don't plan on doing this purification again. We're just going to purify what we have and then kind of move on with our project. And we don't really plan on revisiting and repeating this process. You want to try and maximize the injection on a large column. So maybe you're using a silica column. And since your silica columns are one-time use, these bode well to kind of getting the maximum amount of sample into a single run. And now we have options for, we now offer a 7 kilogram silica column in our REDISEP gold and REDISEP silver material. So you could go ahead and do a batch injection on like a gold column of up to 1.4 kilograms, depending on your the purity, your starting purity, and the resolution of the impurities around it. You could load that much onto that kind of column and purify that amount. Or you're going to do multiple injections on a smaller column, and you could save on column cost, maybe if you're using a reusable stationary phase like your C18, C18AQ, or maybe if it's a high percent organic normal phase separation, you could potentially do multiple separations on back-to-back runs on your large column in normal phase as well, as long as you're not going back down into your low percent organic modifier. Our method development goals at this point would basically be to isolate the target material. We want to focus on resolution around the peak of interest, but we don't have a primary objective to minimize solvent or method length. And the reason for this is because optimizing for solvent method length is going to take time. And we basically just want to kind of get the sample as pure as possible, as fast as possible, move forward, because we're not going to have the time savings accumulated when we do a repetitive purification. So a quick scouting run on the small scale, like with a next gen or an analytical system of your sample, can give you a really good focus gradient, kind of give you a first guess at where your compound's coming out at and what you can do on the flash chromatography. So you want to maximize resolution and then increase the sample loading amount. The default method where you go from 0 or 5 to 10 to 100% doesn't maximize resolution or loading capacity. A lot of that run is time spent where the compound's not moving down the column. So it leads to an increased amount of solvent that's used that isn't necessary for the purification. And it also results in time. And then finally, you can easily scale up from a large column to the large column from a quickly optimized smaller column run. So once you've verified that the purification works on the smaller column, you can easily use a scale-up calculator to transition to that large column. Now, what if we're doing repetitive purifications? So we've got a batch here, that we plan on doing multiple runs on. Maybe we're going to be doing this as a process. It's going to be kind of a daily process for a while or something like that. In this case, our considerations are a little bit different. So if we're doing multiple or continuous batches of sample, we're going to be doing multiple injections. We're looking for really good consistency from run to run. That way we're not scratching our heads when we see peaks moving or things like that, and guessing kind of what our compound is. And then we also going to probably spend more time on method development, and that's going to result in time and cost savings with each future separation. So putting more time in initially is going to result in cost and time savings down the road. So obviously our goal here is to isolate our target material. We want to maximize our throughput at this point because we want an efficient process. We want to minimize the amount of time we're using for subsequent injections. And we're going to really focus on maximizing our optimizing our method and then maximizing our sample loading so that we can minimize solvent use, which cuts down on cost, and our run times, which cuts down on our labor cost. So method development tips for this is we could use a focus gradient generator. We could use our analytical to flash technical note to generate a method that offers us maximum resolution for our compound. Maybe we even consider doing an isocratic method. This eliminates the need to do a column equilibration. It also allows us to maybe even do a solvent recycling outside of the peak. If you have a clean enough compound, you could recycle that solvent and reuse it. And additionally, you may need to also consider doing additional runs to maintain column performance. So if you're using like a reusable column and doing multiple runs on it, maybe we need to do a wash step every 10 runs or so to make sure that we're getting any gunk that's adhering to the column off so we can continue. And so that's something that you do want to consider as part of that process, is any maintenance to your column. So with those kind of questions in mind, so how do we do method development, and then how do we transfer and scale up? And so one of the nice features about the REDISEP line is that you can scale up with REDISEP. So you can do your method development on a UPLC or HPLC column with matching chemistry. And so we have those offerings that match our flash cartridges, it matches our REDISEP prep cartridges, or REDISEP prep columns, sorry. And we can do the initial scouting run on that really small scale. And so this gives us a starting point for method development. It'll generate a focus gradient for you if you follow our analytical to flash guideline, or if you're using an AccuPrep, if you're using the focus gradient generator on that. And that would give you an ideal method there, starting point to do your flash purification. You can even use a quick TLC and use that on a next gen or something like that, and input those TLC values, and it'll suggest an optimized method. What we would want to do then is then transfer that method to our flash column. And so we want to validate that that method performs as well on the flash column as we did on the analytical. And at this point, this is where we want to optimize or fine tune our gradient conditions. Maybe we find we need to modify the %B, or maybe we need to modify the length of the method so that we have sufficient resolution. But we have a good starting point based on our method development on the analytical. The next step would be to determine the loading and volume that gives us baseline resolution. And so we're maximizing our sample loading on that small column now. The next step would be to go ahead and then scale up to the large column. So we would use a scaling procedure that we'll discuss here in a moment, that describes how to scale up from your smaller flash column. So if you have a method on your smaller flash column, how you can scale that up to larger columns, up to 7 kilogram or 8.6 kilogram columns that we offer in our REDISEP material. Now, finally, once you've done that on the large column and you've seen that you've had an efficient, satisfactory purification, now you can go ahead and do multiple injections, potentially depending on your application with the Torrent, if you have a solvent selection valve. We'll discuss that a little bit later about how that can really increase your throughput and efficiency in your process. So for repetitive purifications, here is what we're really going to focus on, because that's where you spend the most time in your method development, and then it's scaling up. So you're going to devote more time to that process so we can repeat the large scale separation more efficiently. But basically, we're going to verify the method on the smaller scale column using the same brand and media. So you want a matching chemistry if you're scaling up. So if you use any of our REDISEP stationary phases, the silver silica, there's a corresponding larger column for that, and the 6 or 7 kilogram column, the gold silica, and then also the gold C18, C18AQ, amine, and C8 media all have matching medias throughout the column sizes. It's the same stationary phase. So if we're converting an existing method from another brand's media, we need to probably just verify that it works on the new brand's media, that there's not any differences in the chemistry of the stationary phase, or and make sure there's not any changes there that we need to maybe modify. But it does give you a starting point. The next thing you need to do is verify that the method on the new media, so we'd run that on the new column, and we would ensure that any potential differences in selectivity are adjusted for. And the new media, especially if you're moving to the REDISEP gold material because of its smaller particle size and the spherical particle shape, this may allow for increased loading because you have better separation efficiency and resolution. The method on the new column may also offer other advantages in the method that would need to be verified. So do we have sufficient baseline resolution? Can we optimize the gradient length and the slope more by shortening it? Shortening the method length to minimize solvent and time. Are we able to maximize the sample loading amount? So can we add more sample? What solvent are we using for injection? How much can we load without influencing the chromatography? So we'll talk about specifically how an injection solvent can really impact your chromatography, and making good choices for injection contribute to good chromatography as it travels down the column. And finally, what's the concentration of the sample that we're loading? And once we've verified that, we can scale up, verify the method on the large column, and then continue and repeat the process. So when we're scaling up to the large column, so assuming that we've done a run on our smaller REDISEP flash columns, if you follow our application note number 121, it describes how you can scale up to the large columns, the large 7 kilogram and 8.6 kilogram columns that we now offer. The best way to do this is really to work in column volumes. Essentially, a compound traveling 1 CV on a small column is also going to travel 1 CV on the large column. The column CVs are provided on the label on the column, so you can always find that information there, or in our REDISEP brochure, that information is there. And then we would then convert the method to minutes, or if the method was in minutes, we would convert that to CVs and then follow a spreadsheet like shown below. And so just kind of a quick overview, you can find this in detail in App Note 121, but basically we're entering the parameters from our first gradient for column A, and then you're looking at your flow rate, what your percent B composition is, what are the segment lengths for the for those changes, and then it'll go ahead and convert based upon the column volume of the larger column that you're doing and generate a new time in minutes for you. So I'm not going to run through the details here. That'll take a little bit too much time. But if you guys go to App Note 121, it offers a spreadsheet here basically with these parameters for you guys to plug in and then generate that information so that you can scale from a smaller column to a larger column in minutes. But the easiest way is really to stay in CVs, and then you don't have to go through this calculation. So one of the important considerations here, and it really has a big impact on our performance of our separation, is how much compound we can get on there. And so we want to be able to maximize the loading amount for our stationary phase. And this is the easiest way for us to increase our throughput. And so for general sample loading parameters for our columns, the mass of sample to the mass of column media for our functionalized media is about 0.1 to 2%. So if I'm running on a 100-gram C18 column, I could run potentially up to about 2 grams of compound on there, so 2%, depending on resolution and how close the impurities are. If I'm using bare silica, we can go up to 20% for the bare silica. So for your REDISEP Gold, you can go up to 20% loading with its higher resolution offered from its spherical particle size and smaller particle size. But these are really just starting points though. If you have a method with sufficient baseline resolution, you can load more material. So we have some examples where in the CBD industry, they're really trying to remediate THC from the CBD oil. So they're not really concerned about isolating CBD, they're concerned about removing the THC from it. And these customers, we found they can actually load up to 10% of the column size in reverse phase, which is 5 times more than what the column guidelines are. And part of that's because of what their purification requirements are. They're not trying to isolate a single compound, they're trying to remove a compound. So there's a little bit more leeway there. But as a general rule of thumb, you can scale proportionally from the size of the method development run to the large column. For example, if you're doing a 100-gram C18 gold column and you've loaded 2 grams onto that column, then if you were to scale up to a 415-gram column, you could load 6.6 grams. If you load up to the 3.8 kilogram column, you could load 76 grams. And if you scaled up to the largest column we offer, the 8.6 kilogram column, you could load up to 189 grams of sample. Keep in mind, this is functionalized C18. So the sample loading is traditionally lower than we find for silica. So if you're on a silica column, you would be able to load up significantly more as a maximum there, depending on your purification. So what kind of potential issues should we be concerned about when scaling up? And so I think one of the bigger things that we do is as we scale up, we obviously increase our injection volume. And so we should be aware of that, of the solvent effects for injection there. And so this can have the dissolution solvent can have a major impact on your chromatography. We've found that doing large dilute volumes in a weak solvent doesn't cause the compound to travel down the column. It kind of sits on top there. And we find this is very common peptide and oligonucleotide purifications where they'll load just a very dilute sample. We're talking about liters onto prep columns, and it just sits at the top and then it travels down once the gradient begins, and they can load a lot of sample that way. If they were to load that into a stronger sample, it would begin to travel down the column, and they'd have some initial band broadening that would be exacerbated as the compound travels down the column, and that's makes for a difficult purification. In general, the ideal situation is always to load in a solvent that's weaker than the starting chromatography conditions. Usually this is the exception and not the norm, as solubility is always a constant battle with our compounds and our chromatography. One of the nice things about the Torrent, though, is it does make it easier to load large sample volumes by using either a sample loading pump or the solvent select valve. Is we can automate that loading process and load large dilute volumes onto the system. Some other tricks to reduce peak broadening from loading is you can dilute the dissolution solvent with the weaker A solvent before we load it. So go ahead and dissolve your sample and then kind of weaken it by adding A solvent to it before you load it. As long as it doesn't precipitate out or you don't have any other solubility issues. Other things you can do is actually you can equilibrate on the column in a slightly weaker solvent than the starting conditions. And so if you do this, what happens is that as you load that strong solvent dissolved compound onto the column, it's going to naturally kind of dilute on the column. And we've had some success doing this in some purifications where there's higher % B starting conditions, and the weaker column equilibration helps to dilute the strength of the injection solvent essentially. Just to kind of visualize this example, this is on our smaller columns, but it's a really good visual example because you can see through the column and you can see the band broadening just based upon the dissolution solvent of choice. So on the left here, we have a strong solvent injection of this compound. And you can see as the picture was taken there, that's right after the injection. The compound's already traveled almost all the way down the column visually. And you can see a pretty wide peak in the chromatogram there with some fronting of the sample. Now, if we take that same picture and we dissolve that sample in a weak solvent, right? That first picture there shows the column right after loading there. You don't see any of the compound. It's all well contained to the top of the column. And then as the gradient begins to hit the column, you'll see that we have a much smaller, much narrower band visually down the column. And that translates to a much smaller peak at the flow cell there in the chromatogram. And so, you go from a peak that begins about probably at 12 minutes and ends at about 18, so a 6-minute peak to a 3-minute peak. So it essentially is about half the bandwidth. And that's going to be, contributing to the resolution of your purification. So as another example here this is from our prep HPLC, but this is another good example of alternate dissolution solvents for compounds. And so prep HPLC, a lot of people like to use DMSO as a dissolution solvent because it has very strong solubility properties, but it is also a very strong solvent in our reverse phase chromatography. So it wants to push compounds down the column. And so in this case, we have a polar compound. In the top example here, we have it dissolved in 1 milliliter of DMSO, and that first peak there is the DMSO peak. And then peaks 2 and 3 are compounds of interest there. And you'll see at 1 milliliter of DMSO, we can go ahead and load our sample and we get baseline resolution still. So this would be a satisfactory purification. However, when we try to maximize the loading of the sample there and increase our dissolution or our sample loading to 2.5 milliliters of sample dissolved in DMSO with the same concentration, you'll see a lot more peak fronting there. And we actually start to see the peaks coelute. We don't have baseline resolution. We also start to lose some of the front of the the first peak to the DMSO. So it's actually smearing and kind of in front of that peak. And so that's not a satisfactory chromatogram. It's not going to be a good purification for us. So we're going to do the same separation this time in the sample dissolved in water. And I'll preface this with, yeah, I mean, this is ideal that we're able to dissolve our sample both in DMSO and water, but this is a really good illustration of the point of the loading capacity being increased when we dissolve the sample in water, because we're able to load more volume. And so on the left here, we have our purification dissolved in DMSO, the 2.5 mils. We don't have baseline resolution. When we have that same concentration of sample dissolved in water on the top right there, you can see we don't have the DMSO peak 1, which is great, but we ultimately have baseline resolution between peaks 2 and 3 here, or what, peaks 1 and 2 now on our sample. And we've loaded the same amount of compound as we did for the 2.5 milliliter injection in DMSO. We still have baseline resolution, and we can go ahead and actually maximize this and load up to 4 milliliters of our sample dissolved in water in the lower right chromatogram there, and still have baseline resolution. So we've been able to maximize our loading by changing from DMSO to water, and have 4 times the amount of sample loading per run with this change in solvent. So how does this translate to the torrent? So large scale purifications we perform on our torrent flash chromatography system here. It's good to understand the different loading options here. And so you do have 2 options in flash that we don't have in prep HPLC. And one is liquid injection via the syringe, which is similar to prep. And then the second option here would be using a solid load cartridge. And so the injection valve on the torrent enables you to automate your column equilibration, your sample loading, the purification process, air purge, post-run valve cleaning, and you can truly walk away once you set the run up. The solid load cartridges is an additional benefit for flash chromatography, because this is a really great way to minimize the effect from dissolution solvent, because we've already dry loaded our compound onto a stationary phase and removed that solvent. And so we remove essentially all contribution to the loading effect by using solid load cartridges. And the torrent allows you to do sizes up to 750 grams of compound loaded onto a solid load cartridge. It is also, there's also pre-packed with C18 up to 65 grams there. The other thing you can use these guard columns for is to protect your large column investment. If you're using alternate stationary phases, you can use that cartridge as a guard column essentially. So, because it's absorbing all the stuff that would accumulate at the frit of your column. So on the torrent here, just to kind of walk you through what the software looks like when you're doing your loading. So when you begin your run, you've set up your gradient and everything, and you hit play on our system. The loading options screen is going to show up here. This is the minimum running requirement screen also. And basically, it's going to tell us the necessary solvent requirements. So how much solvent do we need? How much waste are we going to produce? It's going to allow us to set up our fraction collection. And it has an RF, if we're using a FOXY, it will identify the RFID tags on those racks. So you know which rack is what on the FOXY. Additionally, it's going to give you these different sample loading options. So it's going to allow you to do solid load cartridge with a pause. And basically what that's going to do is it's going to pause after equilibration. It's going to give you the option after the equilibration, the system's going to pause. It's going to allow you to place the solid load cartridge on there. So then you can go ahead and then begin the run. It allows you to maximize the time during equilibration to prep your sample. You could choose the solid option, and that's if you already had your sample prepared, you got your solid load cartridge on the system. It'll automatically go ahead and do your equilibration and then begin the run through the solid load cartridge. If you do liquid injection, it's going to do the equilibration, pause until you've loaded your sample via the syringe, and then begin the run once you're ready. And then finally, maybe your compound's directly on the column already, or you've loaded your compound on a column another way. You can choose none on column, and it's going to begin the run right away without an equilibration. So how can we get more out of large scale separations with the Torrent? And so we have two different options here. We have the Torrent AQ, and these basically give you, the Torrent gives you a large scale flash purification that enables either normal or reverse phase separations. And the Torrent AQ is a system that's dedicated to purely reverse phase separations. And the reason for the two different options is that the Torrent AQ has different pump material used in it. So it has a longer lifetime if you're doing purely reverse phase separations, and it minimizes the downtime from having to do maintenance and preventative maintenance and maintain the pumps. The additional solvent selection valve is an option. Solvent selection valve module here allows you to perform advanced separations with 2 B solvents. So it adds a B solvent to the, gives you B1 and a B2 solvent, and a sample inlet line. All of them with active solvent level sensing. And so that allows you to do multiple sequential purifications of the same sample without user interaction, and then allows increased throughput. Additionally, it allows you to do more complex methods. Maybe you need to do a solvent change from B1 to B2, or you need to do like a column wash, and you can automate that process with the solvent selection valve module. Additionally, there's been continual innovation with new features with the PeakTrack software. One of those improvements is the ability to use the solvent selection valve module and then do automated injection of automated multiple injections of the same sample. And you can increase your throughput by allowing unattended operation and process large sample batches. And then just recently, we've expanded our line of large columns to include 8.6 kilogram columns in the REDISEP Gold C8, C18, C18AQ, and amine medias. So you can scale up to that size column. And then additionally, there's in that same column body is a 6.8 kilogram REDISEP Gold silica and silver silica column options. So you can scale up on the normal phase as well. And to minimize, that allows you to minimize the number of purifications you need to do, so you can save some time in setting up your purification there. The Torrent is a great tool for this. It allows binary gradients from 0 to 100% to include solvents like water, acetonitrile, methanol, DCM, hexanes, ethyl acetate, many more. It goes up to 1 liter a minute. But the binary gradient capabilities allow you to do advanced purifications with maybe a focus gradient. You could do step gradients without having to use premixed solvents, things like that. The new column sizes allow us to purify up to 1.4 kilograms per run. That would be like on a REDISEP Gold material, the silica material. And higher flow rates mean the larger columns that we can use on the system. This increases our sample loading capacity, increases our throughput. PeakTrack software is built on the same software we use for our other systems, including like the ComboFlash Next Gen or even our AccuPrep and AccuPrep SFC. These are known to be easy to use user interfaces for walk up and go purifications. And we can easily transition from a Next Gen to a Torrent with the PeakTrack software. Additionally, there's active solvent waste level sensing, so you can walk away from your system and not be concerned about solvent overflowing your waste container or running out of solvent with your input solvents. The Torrent has a really compact design compared to other systems, so we can fit that on a bench, so it fits on a lab bench. And then finally, you can configure it to meet your scale and purification needs. So there's multiple different modules, including fractionation valves, fractionation racks, open bed fraction collector, and then sample introduction techniques to meet your unique lab needs. When we're doing scale up, some important safety considerations and features to consider for your system. The Torrent has a vapor sensor, so if there's any leaks, it'll stop the system automatically until the leak is resolved by the user, and then it can continue. So that's obviously a very good safety feature. Pressure sensors, so if you have a blockage in the column, it's going to slow the flow down or stop the pumps completely so that you don't have any overpressure issues with your column body. Air purge for easy disposal of columns, so you can get that solvent off the column before you remove it from the system. Makes less mess and makes the columns easier to handle. There's an audible alarm when user intervention is required. removable washable drain tray that you can clean easily. The system also has static dissipative tubing throughout for the high flow rates that you're using. And the patented level sensing ensures adequate solvent for purification and prevents waste overflow and messes that way. And you can easily network the system and watch the progress from any location. So the different fraction collection options here for the Torrent, depending on your scale. So if you're doing smaller scale columns, a lot of times you're going to be using open bed fraction collection. You can do that on the Torrent. You can do that into 25mm test tubes or other options. And you can also do it in 2 bottles, like in the picture shown here. And this uses the same RFID rack identification technology that we use in our other systems. The system's automatically going to recognize the rack that's on the system, and set your fraction collection parameters for that rack. So you're not going to overflow the tubes or the bottles. You can also use funnel racks on these systems if you want to collect larger quantities and go into your own bottles. And you can collect based on volume with triggers, from detected thresholds, slope, or time settings from your UV vis signal or ELSD, if you have that option. This is really good for method development and validation because you get that open bed fractionation where you can check the fractions when you're done, and you can establish time windows on a scaled up column if you're doing a repetitive process. The other option is the Torrent fractionation valve here. So it's a 6-port valve, allows you to collect into 6 different fractions. You can set up time windows for these fractions, and you can also it has a separate waistline in addition to that. Collect on the same parameters as before. This is really great if you're doing repetitive processes, if you have defined fractions and stable chromatography, and you can collect into the same vessel from run to run for those unique fractions. So fraction 1 would always go into tube 1 for each run, and so on and so forth. And then finally, the other thing to think about, like we said, is the column options for the system. And the Torrent pairs well with our REDISEP and REDISEP Gold column offerings. RFID sensors on the columns. The tags will automatically load the method for the column, and you can run from 80-gram columns up to 8.6-kilogram columns on the Torrent. Additionally, this is going to track column use information on the RFID tag, so you know what column, what solvent was on the column last, how many uses it's had, when it was first used. Important information when you're using a multi-use column like the C18 or C18AQ media. The 750-gram, 1.5 kilo, and 3-gram columns all have large inlets and outlets to minimize flow restriction. And the large 6.8 and 8.6 kilogram columns have tubing kits to connect them next to the system here. So we can easily scale up methods from smaller systems. Smaller columns ran on the smaller combo flash next gen systems or RF systems. And like I've said before, the 8.6 kilogram column is now offered in all of our gold medias, the C18, C18AQ, C8 and amine columns. And the same column body is used to offer 7 kilogram REDISEP Gold and silver silica columns. So now those are all offered as new products this year. These REDISEP columns can also fit on other competitor systems. There's a good technical note describing how to connect those columns to other systems online. So finally, I want to go into the automatic sample loading to increase your throughput and how the solvent selection valve can help you facilitate that. And so automated loading process on the Torrent is a little bit different than the other injection or the other sample introduction methods that we discussed earlier. And so just to highlight the difference in the screen, so you're going to get your run requirement screen when you hit play. And if you have the solvent selection valve on there, you're going to get this option. And when you select your sample loading technique, you would choose automatic. And when you do so, you do get some additional parameters you need to enter. And some of those things are the total sample you plan to sample volume that you're going to purify. Okay. And then the total number of purifications you're gonna do. And then based on that, the Torrent's gonna determine what your injection volume is and then apply that to each run. The third parameter here is really useful if you have maybe more viscous solvent you're loading your sample on. You can reduce the flow rate for the injection during the injection process as you load that on, so you don't overpressurize your column. The torrent selection valve here is pictured here. Like I said, the capabilities of this is this adds an additional B solvent to the system. So now we have a B1 and a B2 solvent. And this allows us to do any binary gradient between our A solvent and our B1 or B2 solvent. We can change from B1 to B2 or vice versa in the run. This allows us to change solvents depending on our purification needs. And it also adds a sample inlet line for liquid loading sample into the column using the B pump. And so this introduces the ability to run sequential injection of the same sample without user input. Some sample guidelines here if you're using the Torrent solvent selection valve. And for best chromatography, you're going to want to choose as weak a dissolution solvent as possible, but we need to be sure that it is dissolved. It's really good practice that the sample be free from particulate, as this does go through your B pump. If you send particulate through your B pump, then you're going to reduce the lifetime of that pump and before it needs maintenance again. For some samples, it may be good practice to stir and gently heat the sample to ensure that you have good diffusion and an even concentration of your sample, depending on how your sample maybe dissolves. The other parameter you need to be aware of is that the solvent used for loading needs to be less than 90% hexane to prevent premature B pump failure. Because the B pump on the Torrent is normally doesn't use hexane or alkanes, it is a different material. So you want to be sure that it has less than 90% hexanes in it to prevent premature failure. If you're doing the solvent selection valve with normal phase solvents, it's best used probably for isocratic methods or even gradient methods that don't start at 0% B. And this is because if you take a new column essentially and then expose it to polar solvent, it can change the selectivity of the silica versus a new column when you try and reuse it. Particularly at the 0% B. But if you're doing a method that starts higher where you already have some polar solvent on it, that effect is not as significant. You can kind of use that as a reverse phase column for a short period of time. The other thing you need to keep in mind is the potential for column body swelling with some organic solvents over time. And like I said, you can probably reuse a silica column over the same day, depending on each purification, but I wouldn't use it over multiple days. And finally, some other considerations, things that you'll notice with the solvent selection valve is the manual control features are different. You can add the solvent selection valve to any existing Torrent as long as it has operating system 2. And then you would also need to update PeakTrack to version 2.165 or newer. Some operating guidelines when you're using the solvent selection valve is you would need to use the sample line to manually, or you'll need to use manual control to prime the sample line to the solvent selection valve. Okay, this has clear tubing so you can visualize the sample up to the valve. Once you've primed it, it's good practice to go ahead and flush the air from the lines between the solvent valve and the B pump by performing an auto prime using the B solvent of choice followed by the A solvent. It's also good practice to flush the sample line with B solvent after you're done, and this will prevent precipitation of samples as solvent slowly evaporates without system use. And you would also do that in manual control. This is just an example of our 8.6 kilogram REDISEP gold column, and just to show the performance of it over multiple runs and how the consistency. And so this is an application of the purification of CBD concentrate to remove unwanted THC. And so what they're really interested in here is the first fraction here that's highlighted between 1 and 2. That's their CBD fraction. This is a 10% sample loading on the 8.6 kilogram gold column, C18 column. They're loading 1.6 liters of sample onto this column per run. And this would be run 1 versus run 20 there. You can see that the performance of the column is still satisfactory where they're doing multiple runs. They're removing that final peak, that THC peak from their CBD mixture so that it's compliant, and the column performing very well. And they're using the solvent selection valve to be able to do this process over multiple runs and multiple injections. So finally, just a summary of what we've discussed today. So we've discussed considerations for large-scale purifications. Whether we want to do a single batch purification or are we doing repetitive purification performed many times. Explain some differences to consider when moving up from small scale to large scale, including your loading sample, your dissolution solvent, considerations to maybe optimize the method further if you're doing multiple large scale purifications versus doing a small scale purification, those kinds of considerations. We've described the process to follow up, describe the process to follow to scale up to large scale columns. So we've highlighted tools such as our analytical to flash technical note to generate focus gradients, or the focus gradient generator on the AccuPrep as part of method development. We've walked through how to scale up the large scale column based upon our existing scale up method using application note 121. Go to that application note, and it'll describe how to do that. We've showcased our larger column offerings that allow for increased sample loading and increasing our efficiency and throughput. So we have our 6.8 and 8.6 kilogram column offerings now. And we've got various medias, including the REDISEP Gold Silica, C18, C18AQ, C8 and amine column offerings now. And also the REDISEP Silver Silica, which all of these allow increased sample loading with the same performance and selectivity as our smaller REDISEP offerings. And then finally, we discussed how we can perform automated loading for multiple injections, and how introducing the Torrent solvent selection valve module can enable users to perform multiple unattended separations of the same sample. And this really offers us true large-scale purification with high throughput and efficiency with minimal user interaction. So the user can be doing other tasks while the runs are going, and we can maximize their efficiency in the lab. And so with that, thanks for joining us today. Feel free to follow us on social media. You can find us on Facebook, /Teledyne-ISCO, on Twitter @Teledyne-ISCO, on LinkedIn, /Teledyne-ISCO, and on YouTube with /Teledyne-ISCO. And with that, we'd like to open it up to any questions. So one of the first questions is, if we're doing multiple injections sequentially on a column, do you need to wash the column prior to each new injection? And this kind of depends on the separation. So if you have a fairly clean, you have a fairly clean product you're putting on there and you're purifying maybe 2 or 3 materials and nothing's being retained on the column, then you probably don't need to do a wash step every time. You may need to do like a wash step every 5 or 10 runs or something like that. And that's all going to be compound dependent and sample dependent. The nice thing is that you can build that wash step into your method. If you do need to do that every single run, you can do that at the tail end. And if you're doing sequential injections with like the solvent selection valve, you have the B1 and the B2 solvent, and you can automatically switch from, say you're doing a water methanol gradient, you could then switch to like a stronger solvent like acetone to do the column wash at the end of each run as part of the method. So you can build that in easily with the Peak Track software and the solvent selection valve. So that's a really good question, but it is sample dependent. Sometimes you don't need to do that wash every time, and you can save solvent by doing that wash maybe at the end of a series of injections instead to make sure that your column's clean and ready to go for next time. Another question here that is what do we mean by the weak solvent? And so since the system's used both in normal and reverse phase, in normal phase separations, traditionally our weak solvent is something like hexane, or it's going to be the non-polar solvent, and our strong solvent is going to be a polar or more polar solvent. Now, when we get into reverse phase, our we're using water as kind of our weak solvent in that case, and then our organic modifier would be our stronger solvent. So that's what we mean by weak solvent. Just depends on whether you're doing normal phase or reverse phase, but the same principles are going to kind of apply as you increase solvent strength throughout the run. So another question is, how much does the cycle of the runtime affect the separation? And so this is something you would probably determine on the small scale column before you scale up, and where you're establishing your loading parameters and your method optimization. And so, the key there is we want to be able to have a long enough separation at a certain percent B composition or gradient where we get baseline resolution between our compounds. And so that's really what's going to dictate your, how long your runtime is, and the cycle essentially for each injection, because it's going to be sequential of that same method. Another question here is the customer here has a late eluting purification here. So their compound is coming off about 85–95% methanol. They'd like to save solvent and reduce their method time. So what is a way for them to do that? Well, it kind of depends on, I don't know what the exact gradient conditions you're using, but if you're starting like at 5% B and using a default gradient and your compounds are eluting late, you could just basically do a purification from 75 to 100% or something like that. Right before you kind of choose the point right before your compounds start to actually travel down the column. Hypothetically, if the compounds are coming up late enough, they don't start coming out until about 85% or so. That gradient from 5 to 85% is not really contributing in any baseline separation of your compounds and your close impurities. And so that's somewhere you can save quite a bit of solvent. You're not going to save as much organic solvent at that point. You're going to be saving more water, and you're going to be having a faster method. But that's one way that you can shorten your method time by optimizing that initial gradient. And that's why it's so important, if you're doing multiple separations of the same or similar compounds, is to determine a method optimization that works well for that class of compounds or that specific compound that you're going to reuse multiple times when you scale up. And the time savings are going to kind of multiply with each injection that you do. Another question here is, does the Torrent system need to be grounded? So it does. It's grounded through the electrical ground of the power supply to the outlet. So that's one ground, and it does have a grounding location that you could ground to another ground point in your hood or on your bench. So you can do that. Usually we kind of defer to what the local requirements are, but you're able to do that. But it is inherently grounded through the power supply also. Another great question here. So we mentioned our silver line of columns now, REDISEP silver. And so that is the, it's the same material that was formerly just the regular REDISEP. So now it's REDISEP silver. So we have the REDISEP gold, and then we have the REDISEP silver available now. So they would have a silver cap now. They used to have a clear cap. So when you actually see those, you would be seeing silver caps on those now. So that's a really good question. It's the same material. Another really good question here is how to wash the system between two different polarity mobile phases, or if we're going from organic to normal phase kind of use. So the manual control screen is really important in this case, because you need to flush out the entire flow path with a miscible solvent. IPA is a great choice because it's miscible between water and hexane. And you can kind of do that, flush the system with IPA and then switch to your new weak solvent. Otherwise, you kind of have to go sequentially through miscible solvents. So like hexane to ethyl acetate to methanol to water. It's a little bit more complicated. So IPA is a great solvent to use. Just make sure that you flush all the flow paths and both sides of the pump, the A and the B pump, depending on what you're using. Let's see here. Had one last question here. And then there's a couple I'll answer directly to the customer later here. they're pretty specific. I need a little bit more details, but you know, is it common to see your product come out in 2 different retention times? And then I'd say it's not, you know, this happens sometimes. Usually what happens is we'll have kind of different, maybe you have the neutral compound and the charged compound, maybe in equilibrium under the solvent conditions that you're running at. And so a lot of times if you add an acid or a basic modifier to that, then you kind of force that equilibrium to the to one state or the other. And then that way you'll be able to essentially kind of retain one peak or see one peak retention on there. So that's something that acidic or basic modifiers could help kind of clean up the resolution. If you know that it's the same compound, you know, it could be one is charged and one is not, and you can change the solvent conditions to do that. So I need to wrap up here, and appreciate your guys' time today. A lot of great questions. Feel free to reach out with any other questions to me directly here, joshua.lovell@teledyne.com. And we hope you guys have a good rest of your day.